So I hope my screen is also visible. As it drives power electronics, battery, and charging infrastructure. Right. So these are the four main topics which we wanted to discuss in coming lectures. I mean, drives we will not discuss here because drives we have separate chapter or separate book for a particular that is a separate subject, I would say. But power electronics, battery, and charging infrastructure that has been integrated along with the electric vehicle. So whenever we are talking about the charging infrastructure, the power electronics is automatically integrated in charging infrastructure, right? And battery also the part of this electric vehicle. So power electronics, battery, and charging infrastructure that are the important or integral part of this EV. Now, as we talk about the charging infrastructure, that can be categorized as a level 1, level 2, level 3 charging infrastructure. On-board chargers, off-board charging infrastructure. So off-board, whenever we are talking about the off-board charging infrastructure, that is high-power charging infrastructure, right? However, if we talk about the small or we can say home-based charging infrastructure, so that is 230 to 16 ampere, right? Not more than that. Right? 16 ampere maximum from a single phase socket, we can draw a maximum current that is 16 ampere. Right? So this way we discuss the importance of charging infrastructure, and then we discuss the application of power electronics in electric vehicle. So the application of power electronics in electric vehicle, it is integrated in a two form. One is rectifier form and another one is inverter form. VSI, voltage source inverter form. So VSI, voltage source inverter, that has been used to drive the induction machine, to drive the BLDC motor, to drive the PMSM, permanent magnet synchronous machine. And if you talk about drives, there are three basic machines, BLDC, PMSM, and induction machines, which are widely used in case of electric vehicle. Right? So these three drives are operated through voltage source inverter. All these three drives, they have been operated through electric vehicle only. I mean through VSI only. So 6-leg inverter people are using. I can draw here 6-leg inverter. So what is inverter? Anyone? What is inverter? That is converting DC power into the AC. Right? DC into AC. Like this. So you have DC and we have to convert it into AC. So we have A, B, and C. There is single phase inverter as well, means we have DC source, and again only 2 leg can be utilized in case of single phase inverter. So here we have A and B. In between A and B you can connect any load, any AC load, I would say. So if you have single phase induction machine, you can connect between A and B. If you have 3-phase AC machine, you can connect between A, B, and C. These 3-phase inverter you can utilize for that. Are you able to get it? So under this, we discuss the various factors. Then we discuss how do we use battery energy storage in electric vehicle as well as high power charging stations. Suppose in a charging station, the renewable is also integrated. The solar and wind both have been integrated in a particular charging station. Renewables are uncertain in nature. Renewables, they are uncertain in nature. They cannot, you cannot say, they are variable source. Sometimes they are producing electricity like wind. Out of 24 hours, for 6 hours the wind is blowing, but next 6 hours there is no wind. So you will get power only for 6 hours because wind is available only 6 hour duration out of 24 hours. So what is the solution? Because as a consumer or customer, I would say, please provide the 24 or into 7 electricity to me. It is not like that 2 hour electricity you are provided, but next 2 hours there is no electricity. No one will accept this kind of power generation. Right? Therefore, what we have to do? What is the solution? We have to provide the battery bank along with the solar wind based charging station. So that, and one of my research scholar, Dr. Duri Chanjarani, he has proposed multi-spot based charging station. He has integrated, he has published in IEEE transactions, he has published 4 to 5 IEEE transactions paper. I hope everybody is aware about IEEE transactions that are very reputed journals. And if you are having good work if you are doing research and you have done a substantial contribution in that research, you can publish in these journals. They are really reputed, and world are appreciating if you have done any work. World appreciates if you have done any significant work and you have published these IEEE journals, IEEE transactions. So he has done substantial work, and right now he's working in one of the R&D team at Indore. Sati Pump, if you heard the name, they are developing different machines for electric vehicles as well as for water pumping applications. So he has developed this multi-spot based charging station. One of the key area, those who wanted to do research in electric vehicle, I would suggest please explore this area where you can have a microgrid integrated charging station. What kind of charging station? Microgrid integrated charging station. Let me write a 9 point, which is very important. Microgrid integrated charging system. Have you heard this name? Anyone? Have you heard this name? Microgrid integrated charging infrastructure. So what we have done in this, in the work of that particular student, we have different sources, solar, wind, and the grid. And these three sources are integrated along with the battery. Right? So in the coming hours, if today time permits, then we will talk about this. I will show you one of the configuration where this type of analysis we have done. We have connected solar at DC bus. We have connected a battery bank at DC bus. We have connected different electric vehicle DC bus, and we have connected the grid via this VSI. This VSI we have connected the AC grid. So this kind of charging station, it is very famous because it has two sources. I would not say only two, three sources. Suppose we have a petrol pump kind of station, filling station, and in petrol pump we are getting 24-hour this petrol, right? Even though daytime, nighttime, whenever I'm approaching these petrol pumps to get the fuel, then the fuel always it is available. So in a line in the same particular manner, what we have to do, we have to provide the charging to a particular customer in a charging station as well. I cannot say like we don't have electricity, so I cannot provide you with the charging. So that's why we have integrated solar, wind as well as battery bank. One battery bank is integrated so that whenever solar, wind is absent, solar, wind are not there, grid is not there. So this battery bank can supply the required amount of power to the EV battery. Right? So that was the scenario which we discussed in last particular lecture. And then we discussed few case studies. We started with the case studies, right? Because we need to understand the basics, then we can proceed, we can dive in the topic. But without understanding the basic points, what are the batteries, how do we charge the batteries, how do we discharge the battery, how do we connect these batteries to the, to the AC sources, what are the kind of devices which is required to connect these sources to the sources. Infrastructure. Then we compare these two machines which are widely used in the charging infrastructure, PMS and BLDC. And then we have seen what is the domestic charger, what is the rating of domestic charger, right? And what is the public charging infrastructure? If we talk about public charging infrastructure, they have been categorized into three parts, L1, L2, L3, right? Means level 1, level 2, level 3, like that. And there is semi-fast charger as well, semi-fast charger. So we were having these key points which we need to discuss under this particular topic or this particular slide. So we have EVCs, electric vehicle supply equipment. These are the few components which are related to, which are the essential part of electric vehicle supply equipment. Energy efficient transfer, efficient thermal management, better SOC estimation, right? Improved battery performance, extended battery lifespan, better energy utilization, safety, reliability, consistent pack performance, all has to be integrated in a particular charger. And after that, we started our discussion on battery. So battery has various parameters starting from voltage, ampere hour, watt hour. You will not see the battery rating which is given in ampere only. It is always given in ampere hour. Why it is always given in ampere hour? Because we have to see how much backup it can provide for a particular current. Suppose it is written 10 ampere hour. So according to the C rate, what is the capacity of the battery, or for how many hours this battery can be last longer? Right? If I'm discharging, obviously it will depend on the discharging rate as well. We cannot say only it will depend on the ampere hour which is given. But suppose you are discharging the battery with a 20 ampere hour. However, the rating of the battery is 10 ampere hour only. So you are drawing the double of the current of its rated value. So it will quickly discharge, right? If it is last longer for 1 hour, with a 10 ampere current and you are drawing 20 amperes, so it will last longer for only half an hour. Therefore, we need to understand load management. We need to do the load shedding so that the battery ampere hour capacity can be saved and this battery can be utilized for longer. Then we have state of charge, DOD, SOH, state of health. Then series parallel combination of battery we have discussed. Suppose I have electric vehicle which require 24 volt battery, 48 volt battery, but we have 12 volt and 100 ampere hours. So what we can do? We can connect it in series, right? To get 60 volt, 48 volt, whatever the voltage it is required. 4 volt, 4 batteries can be connected in series in that case. But current would remain same. Current we cannot change. To change the current, we can connect these batteries in the parallel. So that 100 ampere hour can be produced by one battery. Second battery can produce another 100 ampere hour. So total 200 ampere hour current can be supplied from a particular source. Now we had 3 basic questions. What is fully discharged? If we are talking about 12 hour 100 ampere hour battery, so what is the fully charged? What is the fully discharged voltage? And then at what rate we can charge these batteries? Right? And then we have seen one more case study. And this case study belongs to, if I have given you a DC power supply, now I'm saying charge this battery, set the voltage current limits of a particular DC power supply, try to charge it, right? Try to charge it. And then I told you, otherwise if you switch on S2, a huge current will flow, inverse current will flow because capacitor that is sitting on 0 volt. So 12 minus 0 divided by the impedance offered by this battery, internal resistance offered by the battery. So this may take a very longer and very risky and very high interest current can be drawn by this capacitor, and that can damage the switches of this DC current. So that we have to avoid. First, we need to charge these capacitor up to some extent, and then we can switch on S2 so that the current can take place from capacitor to the battery, not from battery to the capacitor. So that was the main discussion which we had in last lecture. And then we have seen the charger one, how we decide the charging rating, charger rating. Though battery is rated only for 560 watt. And then we have discussed the two-wheeler, why this there is fire and other problems. EVCS classifications. So EVCS, that is fixed charging station, mobile charging station, battery swapping, and then wireless charging system. So battery swapping station, that is quite difficult for 4-wheeler, buses, trucks. For heavy vehicle, it is difficult, whether you need to have the proper manpower, or what you have to do, you have to take help from robot or some other instrument which can directly change this battery without harming the vehicle or opening and closing this particular vehicle. And then we have wireless charging system. So wireless charging system is categorized into 2 parts, that is static and dynamic. So static, which I told you, what is the static charging station? The static charging station is we have some coils which are, so there are 2 types of coils. One is transmitter coil and another one is receiving coil. So transmitter is transmitting the electricity to the another coil, right? So transmitter coil, it is under the, at the charging station, or it is situated in the road while we are talking about the dynamic charging. But in case of static charging, vehicle is standstill. Though there is no physical connection between the charging stations or the coil to the, we can say, the coil to the we don't have any kind of connector gun similar to the this wired based charging. Here we have wireless, right? So charges are transferred from transmitter to receiving coil through via electromagnetic induction. There is electromagnetic induction principle which is transferring this power from at high frequency. Remember, it is not a fundamental frequency transfer, at high frequency. So somebody told me there is always some electromagnetic wave which is the prime concern in the future related to wireless charging infrastructure. Because these are the strong wave. These are not the very, less magnitude of wave which we can talk about for this antenna or wireless power which we are transferring for microphones or some other phones. Here we are talking about the power which is transferred in a kilowatt range, right? So there is always risk of this electromagnetic waves which are very dangerous for humankind. But what we can do, we cannot ignore the technology. Simple thing is there, because this technology is giving wireless charging facilities. You can think about, if you have 180 kilowatt charging station, what would be the size of connector gun as well as the cable? Cable. Size of the connector gun and the size of the cable. Correct? So the magnitude of current is very high in that case. And we have to select the insulation of the cable very carefully. Correct. So that's why this wireless charging system is famous. Now let's discuss another few basic things related to the battery and storage, I would say, right? And then we will talk about the types of chargers and how do we go ahead with the charger. One exercise today we will see, case study we will see what is the charging and other thing related to this battery. So how we have classified the battery? How do we classify the battery? So battery, there are two types. What are those types? There are two types of battery. One is primary cells. The second one is secondary cells. Can you give some example of primary cells? So primary cells, they are known as dry cells. Correct? They are known as dry cells. Like the battery, or we can say these batteries widely utilized in watches, right? Torch and other purposes. I mean, there are a number of applications where dry cells are used. So, what is the example of these dry cells? Zn, zinc, manganese oxide, right? And the second one, which is very famous, that is zinc, aluminum oxide. Right? These are the two examples of a primary cell. Now, what about the secondary cells? What is the example of secondary cells? What is the disadvantage of primary cells? Now, I request TA to provide the mic to the learners so that they can speak and discuss if they are facing any issue. I cannot see the chat box every time. Please, requesting to provide the mic to the learners. Yeah. Naira, can you provide the mics to the learners? Mic access. Right, so we have two types of battery. Let me write the I wrote to the TA. I hope he will provide in a given time span. Like, please provide the mic access immediately. Okay, thank you. Yeah. So there are two types of, I mean, there may be other types as well, but here we are focusing on only two types, and they are known as dry cells. So there are two types. One is zinc manganese oxide and zinc aluminum oxide, Z and Ag. Now, what is the problem with the dry cell? They cannot be, as somebody wrote, they cannot be charged, right? They cannot be charged. So once you are utilizing these cells, these batteries, you have to throw it away, right? They cannot be recharged. However, what is the advantage of secondary cell? These cells can be, yes, charged and discharged several times. So what is the example? Example of secondary cells? UPS, right? Uninterrupted power supply.
For lithium ion.
Yes, so EV batteries, I decide EV battery instead of lithium ion, instead of saying
nickel cadmium.
Let us say I would quote EV battery. Right? So this way, these two types of battery, which are very much famous. I mean, these battery nowadays, they are very famous as the application of electric vehicle point of view. It become very famous, right? Now, we have seen the various types of batteries, which are, I mean, few basic parameters related to batteries. How do we utilize these batteries? So every time, what we have to see, we have to see various parameters related to the secondary cells. We need not to monitor the parameter related to the primary cells, but as I told you in the previous class, for the secondary cells, we have to monitor the capacity of the battery, we have to monitor the SOC, state of charge, we have to monitor the DOD, depth of discharge, C rate we have to monitor, efficiency, very important. Efficiency we have to also monitor. And the last one is energy density and power density. That has also, that has to be monitored in a given lifespan. Like we have to monitor the energy density and power density as well. So these are the features which has to be monitored for a given battery. Now, let's talk about each of these features one by one. Talk about these features one by one. So first talk about the battery capacity. Right? Let's talk about the battery capacity. Then we will slowly talk about the efficiency as well, C rate and DOD. Correct? So first let's talk about the battery capacity. Capacity. So how do we represent the battery capacity?
And there are H.
There is AH. And any other capacity to represent the capacity of the battery?
MAH.
MAH, then you may write MAH or AH, that are both are same. For lower ampere hour battery, we are writing MAH, milliamps. Okay. For higher hour, we are writing higher capacity battery, we are writing as a AH. So
capacity
one of the
stored electrons
yes,
in chemical form.
yes. Now, so we are writing the battery capacity in form of ampere hour, or we are representing this battery capacity in form of watt hour. There are two ways to represent the battery capacity. Right? So suppose I have a battery, one current IB it is flowing from here, and we have the voltage VB. So this current can, whether it can go through this battery and or this battery can supply the current, because the this battery is a bidirectional source. Bidirectional source means it can take the current while it's being charged, and it can supply the current while we are discharging. So we have to define the direction of current. That is very important. So what people are doing? They are taking, if IB that is positive, means the current which is taken from the battery, that is defined as a battery gets charged. Battery gets discharged. Sorry. You may take the, as per your convenience, you can take another this symbol. You may consider the negative sign here as well. There is no necessity. There is no necessity. You have to take the positive sign for discharge. But in my research as well as in my consideration, whatever suppose I'm teaching this course, so I used to consider this battery, if this current is positive, then it means battery is discharged. If we are taking this current as a negative current, right? So I would consider battery which gets charged. Now my question is, how do we represent in form of graph? Suppose we have to plot this IB versus, this is IB versus time. So whenever it is above this zero plane, that is plus IB, and whenever the battery current it is below this plane, minus 10 ampere suppose here and 10 ampere here. So whenever this magnitude of current it is below this zero or the x-axis plot, that is representing the IB negative, and the battery is being charged in that case. Now, by the way, what would be the energy stored in the battery? If I'm saying calculate the energy stored in the battery. Energy stored in the battery. How do we define the energy stored in the battery? Or we can say true capacity. Try to understand true capacity of the battery. True capacity of the battery. How do we represent it?
Voltage into current.
Voltage into voltage into current.
पास देखेंगे
Please mute yourself. Yesterday I also told you. You unmute yourself, ask the question if you have any question, and immediately you mute yourself. I should not hear any background noise. Yes. So energy stored in the battery or true capacity of the battery. How do we find out?
Power into time.
Yes. So how do we define the power?
D into I. V into I power.
We have VB into IB, and we have to take time. And this rate of change of time can happen. I can charge for 1 hour, I can charge for another 1 hour. So what I will take DT here. So generally, how do we write? Integrate it, take VBIB and integrate it within a given time step. But you will look into this expression. VB is almost constant. VB, it is almost constant. Why it is constant? Because suppose we are considering nominal voltage 12 volt, so the lower voltage would be 11.6 or 11.5, whatever you are considering. Higher voltage, it can be charged up to 14.3, 14.4 volt. Correct? So VB is almost constant. So if I'm considering VB constant, right? In most of the cases, they are considering VB constant. Yes? Any question? Subankar, do you have any question? Ask Subankar. So why you have not muted yourself?
Just my mistake, sorry. My mistake,
Okay.
I didn't see that, sorry.
Yeah. Keep in mind, please mute yourself. Otherwise, other will not be able to listen. No issue. Yeah, please. So VB is almost constant, as we have seen here. So what people are doing, they used to consider this VB constant. So if VB is constant, I can calculate the capacity of the battery that is given by in ampere hour. Right? In ampere hour. So I have to integrate only IB with respect to time. So this is another capacity of the battery, but this is not a true capacity of the battery. Remember, this is not a true capacity of the battery. But when it is asking calculate the true capacity of the battery, then we have to take this expression. Try to understand. Whenever we are talking about this, we have to talk about the true capacity. But if it is saying like voltage is almost constant, you can calculate the capacity of the battery, then immediately you can integrate the current with respect to time, and you can tell the capacity of the particular battery. Right? Confusion in battery capacity. How do we determine?
Sir, can you explain in short?
Yeah. What?
Battery.
What you are saying?
So battery capacity, sir. In
Battery?
short, sir.
What I have to explain?
Battery capacity, sir. Overall, sir.
So battery capacity is represented in ampere hour or watt hour. If you are talking about the watt hour, that is true capacity of the battery. True capacity. So in question, it is saying calculate the true capacity of the battery. So we have to calculate watt hour. If it is saying calculate the ampere hour or capacity of the battery, that is simple ampere hour you can calculate. If we are charging the battery, so these two conventions we have to follow. If battery gets discharged, we have to take positive IB. If battery is charged, we have to take negative IB. So how do we calculate the battery capacity, energy stored in the battery, or true capacity? So true capacity can be identified as a epsilon omega h VB into IB dt. This way we can determine the true capacity of the battery. Any confusion in this? How do we determine true capacity of the battery? Right? This way we can determine the true capacity of the battery. If I want to calculate the actual capacity of the battery,
Sir, whatever the time, sir, the capacity means the time also fixed rate, right? Like VB.
yes, that's why we are taking TT along with it.
But time also fixed rate, sir.
Yeah, because how much energy it is stored in the given time span, that is like 0 to t, suppose 0 to 1. Suppose time is 1 hour, so you can integrate from starting from 0 to 1 hour. You can integrate from 0 to 2 hour, like that, because we are integrating with respect to